Alright, we finally got the correlation coefficients. Or we're finally getting to the point where we can actually find the correlation coefficient, which shows us how related the genes are. Are they behaving the same way, different way, everything else. So what we're going to do is we're going to take Mike Smith gene 1. So we're going to put equal sign gene 1. And we're going to multiply it, so that's the star. So it's the shift key above the 8. And then we're going to press gene 2. And we're going to get the answer. And then we're going to do the same thing for patient 2. That star gene 2 equals sign patient 3 star gene 2. And then what we do is we add all these products together. Oop, I forgot to press sum. So equals sum. And we take all these and add them together. And then we take them, and it's basically the average of those sums. So we take this number and divide it by 3. Or you could put in average. We could have skipped this part and just find the average of these. And we get 0.64. And then we do the same thing for gene 1 with gene 3. And then gene 2 and gene 3. So I want you guys to do that. And actually, I'll show it to you so we can do it together. And then you can just copy these down, because I'm not too concerned with the math. I'm more concerned with these numbers, and I want to talk about these numbers when we get done. So equals gene 1 times gene 3 this time equals gene 1 times gene 3 equals gene 1 times gene 3 equals sum. And we want the sum of these, and then we want to take that number and divide it by 3. And then finally we take gene 2 and gene 3, so that times that equals that times that equals gene 2 times gene 3 equals sum. And then we take that number and we divide it by 3. Alright, so now we got our gene expressions. So our correlation coefficients. So what they tell us is gene 1 and gene 2 we have a positive correlation. It's a positive, so that means they are behaving in the same way. So let's look at how they're behaving. So let's go back to our gene expression graph. So you can actually see they're behaving in the same way. Look at the graph. They're both going up in gene expression as we go to patients. And they are both, if this one's on, this one's on. This one's on, this one's on, this one's on, this one's on. Alright, they're both on at the same time. Alright, and they're fairly correlated. So whenever one is on, the other one, gene 2 is on almost at the same rate. This would be highly correlated if these two graphs, these 2 points, were pretty much right on top of each other. But they are still fairly high. They're closer to 1 than they are to 0. So these are, I would say, fairly related. And we only know that they're both on in cancer cells or oncogenes because we looked at that graph. Otherwise, we wouldn't be able to tell if these are on or off. Because you could have two tumor suppressor negative genes that would both be highly correlated. Alright, now this one is behaving, since these two are negative, they are behaving in opposite ways. Alright, this one is just like this one. They're fairly related because it's closer to -1 than it is. Not quite as heavily as this one, but they're fairly related. And then these are almost little to no correlation. So the two that we can find the most about is gene 2 and 3 and 1 and 2. 1 and 3 are not really all that related, but behaving opposite ways. So what does that mean? Well, if we look at our graph again, gene 1, whenever gene 1 is on, gene 2 is off. Whenever gene 1 is on, gene 2 is off. at least in the cancer cells, because these are tumor suppressor here, and they're more expressed in. They're right here. That's showing they're more expressed um, in normal cells than cancer cells. So in the cancer cells, these are on while these are off. And they're pretty much the same way. Same with this one. Whenever this one's on, this one's off. This one's on, this one's off. This one's on, this one's off. Alright, so that's why these both have negative correlations. Now, if you look at R1, so gene 2 is a little bit more correlated to gene 3 than gene 1. And that's just because they're just behaving, they're a little bit closer together. They're behaving in a similar way. Alright, so, but we are, again, all we're trying to do is see, is there a pattern here? So obviously, gene 1 is almost always on in all the patients, and so is gene 2, and gene 3 is almost off in all the patients. But then we can see, all right, is gene 1 affecting gene 2? That's really what we're looking at here with the comparing these two. Is there a pattern between these genes and these genes in the cancer patients? So maybe oncogenes, whenever these genes are on, these are also off, or they're both on and off in the cancer cells. So the ones that are probably most important to study here right now would be gene 2 and 3 and gene 1 and 2, which is kind of weird because now you're still looking at all three genes. But for some reason, these are more heavily correlated than what 1 and 3 are. But these are the two that we're probably going to want to look at more because they have there's a strong pattern. That's all correlation means. A pattern it doesn't mean that one is definitely affecting the other. It just means that there's a pattern, all right, in this cancer cell. So whoever these osteosarcoma patients, for some reason, always have, generally not always, but there's some kind of pattern with gene 2 and gene 3. Again, these aren't very strong. We would want to see something closer to like in the 0.8, 0.9 to really get excited about. But there is a little bit of correlation, so we might want to look at more patients, obviously, to get even probably stronger values. All right, and that's correlation coefficients.